Thank you very much. Thank you very much to the organizers for persevering in this ongoing apocalypse and pushing through with the event. So in a change from the previous talk, I will discuss not the dynamics, right, that leads you to optimum of some functional or fixed point or some vector field, but I will discuss the ground state of that functional. So first, let me introduce what are the functional that I'm talking about. So these are going to be best covering and best polarization. And they work like this. You fix a compact set in a Euclidean space. And then you try to cover it with, actually I have a picture coming up on the next slide, so I will not draw anything. So you're covering, or almost anything. So you're covering this set, compact set A, with little balls. You fix the number of balls. You say, let's say there are n of them, right? And what's the smallest radius that you can still cover the entire set A with these radius rho balls. And then likewise, you consider putting Riesz functions at each of these centers, right? And then you look at the minimum that a sum like this attains on your set. And the idea is to maximize this minimum. Now, the stars I have here and there mean that I do not restrict the configuration in any way. So I just I can let these little balls to run around. Right? They can be outside the set, but of course there is not much point in putting them far away from the set. I still eventually want to cover the set, so it makes sense that they'll be close to it. And so in the same way, I can define the unstarred quantities, right? And the unstarred quantities in what follows will mean that I actually do restrict to the set. So once again, the star means I do not restrict the centers, and absence of star means I do restrict omega n to A. So that would be the unstarred version. Oops. And so now the picture I just promised, right, on the left-hand side, I have covering of this blob with 9 balls. There are 9 of them, yeah, there are 9 of them. And in the right-hand side, I have polarizing the same set with also 9 points. So for comparison, here is a single Riesz function in the dark set, right? So if you think of the Riesz, the inverse power law as how your elimination decays. So the further from the light source, these red dots, you can think of them as light sources. The further from the light source, the less eliminated your set is. And this here is a single point alone in the dark, in the unlit set, and here you have a bunch of them, and they eliminate the set quite well. And these are just for demonstration purposes, so I don't claim that these are optimal or anything, but just so you get some feeling for what's going on. So we discussed these 2 problems. Now, there is heuristic relation between them. So you can think of polarization as a sort of soft covering, right? So basically, if you compare to the previous talk again, this is like the hardcore covering, and this is the soft core covering, if you wish, right? And again, let me emphasize that this is the starred version, so I do not restrict points to the set, and as a result, here I have a little point that sits outside the set, but not too far away from it still. So the idea for us will be to take this n, the cardinality of configuration, and send it to infinity, right? And study what happens to one, the optimal radius as a function of n, the smallest radius that you need to cover the set. And on the other hand, what happens to the maximal lowest value that you achieve in the right-hand side? Right? What is the asymptotic of these quantities as n goes to infinity? So that's our goal. Again, goal n goes to infinity. Feel free to interrupt me. I know we don't have much time left, but it's better to keep it informal. So ask if you have any questions. Now, some backstory is maybe appropriate. Why do we care about n goes to infinity, right? So this maybe requires some justification. So first of all, we like taking n to infinity because it allows us to prove theorems. Okay, that's full disclosure, obviously. But the underlying reason is we're basically measuring how complicated, at least for covering. So this slide discusses covering, by the way, primarily. So let me emphasize that this is for covering only. So covering effectively measures how complicated your set A is. The history is that 1948, Shannon publishes his a mathematical theory of communication, which discusses entropy and complexity of signal and things like that. And Kolmogorov reads Shannon. Well, Kolmogorov also reads other people, such as Hausdorff and a little later, the 20s, Pontryagin and Schnirelman, who all work on similar things, covering sets with balls. So he decides to introduce this notion of geometric entropy, right? He does it a little bit in reverse. So you fix the radius. So here epsilon is effectively the radius. You fix radius and you look at the smallest number of points required to cover your set A while using that radius. And then you take this limit and you look at whether the limit exists. And so this basically means that you study the exponent, the growth, how fast the n epsilon, how fast does it have to grow, right, as a power of, well, 1 over epsilon, I guess I should say. So you study the power that you're supposed to put here, right, to make things work. And Shannon's motivation was, for him, effectively covering is complexity of signal. And so if you transmit an Alex signal that you would like to discretize, you're supposed to put these points, distribute these discrete values in the entire signal range to encode the signal in the best possible way. And so in the 50s, Kolmogorov puts forward this program for studying complexity of compact sets in functional spaces. So this becomes a big area. Subsequently, there are many people working on this. I'll come back to this. What these people are mostly doing are studying complexity of sets in functional spaces, whereas we are lucky to have compact sets in Euclidean space only. Now, in relation to polarization, still some side story. So this is not directly related to covering, but something you can still think of as a soft version of covering. So a related problem. So far we have 2, covering and polarization. Here's the third one, which is useful maybe for some intuition. And you'll see falls under a similar framework. And so the problem that Shannon actually considers is not covering per se. He looks at the expected error. So he transmits an analog signal, right, that he's trying to approximate with a discrete signal. And so he's concerned with coming up with a good discretizing function f that discretizes continuous signal. And the idea is he wants to minimize the expectation, the variance, the variance of the analog signal around its discretized version. And formally, you can think of this as Shannon tries to come up with a discrete measure supported on n points, right? Which in our parlance was this omega n. The discrete measure has to be the closest possible to the continuous measure to the distribution of C. Right? So you have analog signal C, and you approximate its distribution with a continuous measure in some transport distance. So this doesn't look like transport distance here, but this is equivalent, minimizing this object, right? So minimizing this over all discrete measures is equivalent to minimizing Wasserstein distance from the discrete measure, sum of n Dirac masses with some weights, to the continuous probability measure that is the distribution of the signal. Now, this is still something like a soft version of covering. You should think of it that way. Now, as a foreshadowing of what will happen next, I want you to note that these three problems, they are all, in a sense, local. So, say this part of the signal only cares about how far, say you have signal distributed on the line here. This part of the signal here cares only about how far it is from the value of the discretizer at this point, and it doesn't know anything about components of the signal that are far away. So that's the important fact about these. Now, okay, so what is in all this backstory? What was actually known about covering? Right. So let's see. So basically, immediately in the 50s, Kolmogorov and Tikhomirov established that the asymptotics of this optimal covering radius, it exists for Jordan measurable sets. Okay, so if you have a subset of Euclidean space and its boundary has measure 0, then you have asymptotics, which holds with the constant. It depends only on the dimension, and some power of the Hausdorff measure of the set. So this shows you the scaling order of this function, and then it shows that okay, there is actual asymptotics. Then in the 70s, people mostly occupy themselves with studying Shannon's seemingly unrelated problem about, well, as we just discussed, discretizing signals. So that's a separate branch of research. Whereas, as I already mentioned, there is an entire school, entire sequence of papers by different people, Bierman, Solomiak, the likes of Bourgain and so on, who study covering for functional space. So of course these are hard problems, much harder than studying covering on the Euclidean space. But on the other hand, all of these people are basically fighting for estimates like this. So they study A in some functional space, and they're mostly fighting for estimates like these, right? So they are not mostly concerned with the asymptotics. All that they are fighting for is establishing things like upper and lower bounds, right? So they're mostly fighting for things like these. So it's really hard to get something like this in a functional space. But since we are working in the Euclidean space, the idea is, okay, we should be able to push this to all compact subsets of RD, right? This condition of being Jordan measurable really seems redundant. And so Graf Lushdi in 2000, they rediscover the proof of Kolmogorov and Tikhomirov, and they conjecture, okay, this should be done for, all compact subsets of RD. This should work. Meanwhile, what happens in the polarization field? Well, polarization follows a similar development. So these people listed here, which I think are all represented in this workshop, so this is quite remarkable. Combination of some papers in these areas, you can see more recent even than the Graf Lushdi, which maybe attests to the fact that the soft covering, the polarization is harder than the hard covering. So basically they establish an analog of Kolmogorov-Tikhomirov result. So they show asymptotics for Jordan measurable sets. And they show this result as well as limiting distribution of optimal omega n's, optimal configurations. And these papers mostly use Euclidean norm, but you can look at them and see that the argument applies to any norm. So I wasn't maybe, I haven't stated this explicitly, but all of the results that I'm talking about here and below, they all apply to any fixed norm in RD. So, okay, so we have two different lines, two different timelines. One is covering, which was done earlier, which establishes asymptotics on Jordan measurable sets. The other timeline for polarization, which does the same. And two questions remain. So primarily, the important question is, okay, why do we still need this smoothness assumption? Right, so what is going on? So it's the 21st century. We should have this, at least for Euclidean space, right? And the second question, which concerns only polarization. Polarization has this power built into it, and things work only for S bigger than D. Right. So the question is, okay, why is this restriction necessary? So to answer both of these questions, let's talk about sort of common underlying principle that covers both the results about hard core covering and soft core covering, both actual covering and polarization. And the principle is as follows. So see if you can spot a theorem in this slide. Ah, there it is. Here is it. Okay, that's the theorem. So there's a theorem. So I follow the principle one theorem per slide. That's yeah. So the idea is effectively this: any functional, right? It doesn't really matter what is its nature, even. Any functional that takes two things as inputs. It takes configuration and set, right? And the set is compact, so I couldn't, yeah, I'm afraid I couldn't think of anything better to denote compact subsets of a D. Well, so this takes omega n and set as input and produces a number. And you're interested, just as before, in studying the asymptotics and distribution for optima. Okay, so this needs some stars. So you take this functional E omega na, right? And then you minimize it or maximize or do whatever you like. Let's say minimize up to change of sign. You minimize it over omega n, right? And then you study the asymptotics and distribution of optima for large n, provided that the functional has some basic properties. It has to be monotonic in the set, so that if you have two sets and one is a subset of the other, then there is some monotonicity. The direction is irrelevant because you can actually multiply by -1 as you imagine and so on, but there has to be some monotonicity for sets. It has limits on cubes. Here's where you should think, there's the catch. Right? But this functional, it has asymptotics on cubes. And here the star, and I'm sorry for not defining it, so here the star means we're talking about minimizers. So the minimizers on any cube of any size, value of your functional on that, with this rate function has a limit. And finally, if you have two sets that are, positive distance apart, and this is why I asked you to think about the short rangeness previously. If you have two sets that are positive distance apart, that are separated, then you have a property like this. And finally, and this is the more subtle one, if you have two sets which don't differ much, the last one, if you have two sets which are almost the same, say this one and this one, then asymptotics have to be closed. So it turns out that the functionals that we discussed so far, polarization and covering, they both work this way. Well, except for this one, because here for okay, I'm cheating here a little bit. So this is not really, this plus is not really a plus. This for polarization and covering, it's actually minimum and maximum. It can be plus. It actually can be any degree 1 homogeneous function. So okay, just think of it as a plus. It's good enough. So the idea is, if you have two sets which are a positive distance apart, then asymptotics on their union is uniquely defined by asymptotics on each of them individually through a degree 1 homogeneous function. And okay, it happens to be, these happen to be different functions, but these four principles, they apply. In fact, not only to polarization and covering, but also to these to Shannon's functional, the Wasserstein shortest distance between the discrete measure and the continuous measure. Now, of course, these principles, they were hidden there in the literature all the time, right? But as far as we could tell in this paper, basically its contribution is that we suggest this. We suggest take these principles and then just run around and whack every problem with these principles and see if everything falls out. And the conclusion was that we could find these principles in several seemingly unrelated functionals. I'll give some more examples later. Another thing that was kind of surprising to us was that you see here, I just say that the functional, it has limits on cubes. It has asymptotics on cubes for minimizers. And it's not important the way I stated. It's not important what the nature of the limit is, as long as it only depends on the size of the cube. But turned out that if you have a property like this, well, for polarization and covering, again, this plus, you have to replace it with either maximum or minimum. But if you have the short range property and you have this existence of limit, then the function, the type of the function f of a is defined uniquely. It has to be a power of a to the d, and the power is defined uniquely by sigma. So it's I think as written it's sigma minus 1, something like that. So basically, polynomials, power functions, are the only feasible right-hand sides here, assuming that you have a rate function, which is itself polynomial in the left-hand side. It doesn't have to be polynomial, it has to be something close to a polynomial, but close to a power, but that will imply immediately that f is also polynomial. Okay, so where I'm going with this. So we thought of this underlying principle. Okay, this is all great. We saw it applied to these functionals, but what's the conclusion, right? So you have this underlying principle. You see that it applies to, say, covering. Then you work very hard to check that it actually applies to covering. And then, as a result, you have theorems falling out of it. And the theorems are that if you have these properties, if you have asymptotics in cubes and then these nice properties, then you have asymptotics on everything, on all compact subsets of RD, and in fact, also on embedded sets. So this is a workshop about manifolds. As a result of these assumptions, you have existence of asymptotics on manifolds, and also distribution of the minimizers. So once again, the general principles, once you verify them, they imply both asymptotics and distribution, no matter what the underlying set is. And so I just showed you the result about covering, and then the same applies to polarization. So this way you push both timelines to all compact subsets of RD and also subsets, embedded sets in RP. Right? So here P is bigger than D, of course. And so you have embedded sets in high dimension. And you get existence of asymptotics. Basically, you extend the asymptotics to these rough sets. Okay, any questions maybe at this point? I know I have to wrap up soon. So
yeah, but if you allow a question, can I translate what you are saying into your studying, or you are proving the shape independence of the ground state energy of your systems, right? It's a shape.
Yes, in particular that, yes. I guess you're saying, yes, it's independent of shape, it is going to be uniform. Yeah. Yeah, so that's one, exactly, that's one way to think about it. And this is the distribution result that I just mentioned. So regardless of the shape, just like you said, you have a uniform distribution, both for covering and, okay, here I have some undefined things going on. So I'm going to skip this slide very, very quick, lest anyone reads it, because I have some undefined things, I'm afraid. Okay, so here's the promised discussion of, these principles, they apply everywhere. So one of the motivations of, thinking about these principles was this. We noticed that engineers were doing things without proof. So quite a discovery we made there. And things were working for them. This was interesting. And so we noticed that there were these nearest neighbor interactions. So here's a paper that what it basically does is it introduces interaction which goes via Delaunay triangulation. So you have a distribution of points, and they triangulate them, and then they only say that only the connected points will interact, and they arrive at the right distribution. So this doesn't make sense until you start thinking about it in the framework that I just described. Then recall again the Shannon's optimal quantization that I mentioned previously. So I sort of left that timeline, but that timeline progressed in its own, and it basically followed the same lines as polarization and covering. So basically, there is a paper 2004 which establishes asymptotics and distribution for configurations that optimize this best quantization. So these are configurations that quantize continuous measures in the best possible way. And the paper by Gruber, who establishes analogs of these results. You find scaling and so on Jordan measurable sets and manifolds. And of course, there is this paper. It's about the same year, actually. These two papers about the same time. It's just a journal date, which establishes similar results for energies, hypersingular energies. And so hypersingular, by the way, means that the exponent is bigger than d, and the energy means that you look at the double sum. Okay, so you look at all pairs, and you sum up things like this, and you minimize. So this is what we mean by recent. And I'm happy to say that more recently, similar approaches, and even in this workshop, similar approaches were discussed. They were just hidden, right? So Con Salmon last year wrote this paper about packing bound functions, that they call them, theta prime. And Andrew actually mentioned this result, a similar scaling result in which the number of centers in this packing goes to infinity, and certain asymptotics is deduced. So the underlying principle there, the proof is quite similar to what we discussed. And basically, you can trace the same four principles in these functionals. And they also do some remarkable stuff with graph functions on graphs. So not only you can study functions in Euclidean space, but you can also study functions on graphs using this short rangeness. And finally, we just put up a preprint recently where we resolve one of the questions that I mentioned, right? So there was this thing that was unclear, right? So S bigger than D, can we get away from S bigger than D? So we discuss energies, so not quite polarization, but we go below D, which makes recent interaction long range, but we cut it after k nearest neighbors. So each point only feels its k nearest neighbors, say 3 of them, and it doesn't feel this one. You can prove similar statements about asymptotics and distribution. And then I will stop actually here because I'm out of time, but using different methods, we prove similar results for covering and polarization on fractals. And fractals, actually, it's worse because, of course, things remain short range, but you cannot really work as before because there is no translation invariance. It's hard. You cannot translate things within fractals, right? So unrectifiability takes its toll, but using renewal theory, you can prove asymptotics for polarization on fractals as well, for both constrained, unconstrained, and constrained polarization. Finally, I'll just go to conclusions. So what was the moral, right? So what is the takeaway? The takeaway is short range interactions like these can be nice because you can prove things more easily than for long range interactions. So that's great. Practically, these are not few and far between, actually quite the opposite, as I hope I've convinced you. So these come up regularly. Even in physics and chemistry, even in the previous talk, okay, you can think about hard disks as a short range interaction. I don't know how much of what I just told you applies to that case, but that is a sort of short range interaction where you feel only your, only the points nearby. So, and indeed, these packing functions, they were discussed using short range methods. And now, sort of, okay, after all this bright and shiny, and advertising for this method, of course, there are things that you cannot do this way if the short rangeness comes in at different scales. So of course, there are hard things, right? And best illustrated probably by Leonard-Jones potential, where in 3D, yes, you do have, you do have short rangeness, but it comes in at 2 different scales and things are hard. And at this point, I thank you for your attention. And if you have any questions, I have a couple of minutes before I have to teach to answer them. Thank you.